June 2018, question 1. An engineer has plotted a straight line graph based on the results of an investigation. And here is that straight line graph, and indeed it is straight. Let's have a little look at some of the details. Our variables are x and y, that's nice and easy. With a straight line, it'll be y equals mx plus c. And also you'll notice that the grid is scaled for one number for each square. There aren't any units given, so that shouldn't be an issue. Right, let's see what they want us to do. Calculate the gradient of this straight line. Okay, 2 easy marks. In order to do this though and get the marks, I'm going to have to show my working. I'm going to pick 2 points on the line that correspond with intersections of the grid. Here they lie on where the grids have got crosses. I'll make a little triangle. I'm going to look at the up part first, the delta y. Delta y will be 5 minus 3, which is 2. Here, delta x will be 2 minus 1, which is 1. Using these values to get the gradient m, delta y divided by delta x will equal 2 divided by 1, which equals 2. And that's what I'll put on my answer line down here. An alternative format we could have used would have been m equals y1 minus y2 over x1 minus x2, which is, of course, the first y value is 5 and the second one is 3. And when y is 5, x is 2. And when y was 3, x was 1. So these values correspond, and these values correspond. Effectively, 2, 5 is one of the coordinates, and 1, 3 is one of the coordinates. That then gives us 5 minus 3 is 2, 2 minus 1 is 1, positive 2. And that positive part is important because this line goes up rather than coming down. That would have given us a negative gradient. Going up gives us a positive gradient. If I had switched these around, then I might end up, if I'd gotten 1 minus 2, then that would have given me minus 1, and 2 divided by minus 1 would have given me 2, negative 2, sorry. Maybe that's what I wanted if the graph was sloping down. You have to just be careful to keep these the same way around. That's why it's y1 and x1 first, and y2 and x2 first. The coordinates x1 and y1, they go together, and x2 and y2 go together to make up a point. Right, that's not the end of the question though, because over the page we've got the next part, which we'll have to continue with. You'll notice on the paper, at the end of each question, it says like total number of marks for that question. You'll see that here. Total for question 1 is 4 marks. Question 1's not finished. So on this page here, I knew we weren't done because it didn't say that. Okay, so find the equation of the straight line. Okay, looking at the graph, it is a straight line. As I said at the beginning, the form of the straight line is y equals mx plus c. Simply writing that will be enough for a mark in this instance because they wanted you to know that that was the format. But it might not always be, so let's do a bit more to make sure we get all the marks. The first thing is I'm not automatically going to put y and x. It's going to depend on what the variables are in my graph or my scenario. But in this case it is y and x, so they'll be staying the same. And if you remember from before, the gradient, that was m, that's 2, so that m becomes a 2. Then we have the x, and now we've got plus c. I'm not going to put a plus in and then look at the number, in case the number's negative. And I find out that number by looking where on the y-axis the line intersects, and it intersects it here at y is 1, positive 1, so I will put plus 1. Had it been negative, I'd just put take away whatever the number was. And that would be my equation of the straight line. That's all they've asked for, so pop that on the answer line. And we're done. Question 2. The diagram represents a base of a steel storage tank. The base is shaped as a sector of a circle. Looking at that diagram, I can see I've got an angle in degrees and I've got a radius in meters. The first thing to do is to convert 60 degrees into radians. I'm going to do this in the calculator, but I'm going to show my working out in order to get full marks by doing that on the page. That's what I'm going to do. You can do 2 pi divided by 360, but that's the same thing. So 60 times by pi over 180. Double check if I entered that correctly, and that gives me 1.0471. Now I'm not rounding that, I'm just truncating it. There's a 9 after the 1, so it would round to a 2, but I'm just taking the first 5 digits, 5 significant figures. What I'm going to do now is my final answer, I'm going to round it, and that'll be 1.05. And since that is in radians, 1.05 rad, or you could use the little superscript c, and I'm going to give my degree of accuracy. Okay, so that's the first part 1 done. Let's look at part 2 and see what we're asked for. Calculate the area of the base, and that's the sector of the circle. Now in the formula book, we can look up and make a note of the formula. The area of a sector equals 1/2 times by the radius squared times by the angle. We've got the angle. That angle needs to be in radians like we've got here. It states that in the formula book. So don't use a degrees angle in there using this version of the formula. The formula you need to use uses radians. Let's substitute in 1/2 times by the radius, which is 2, squared, times by the angle in radians, 1.05. Now I'm putting down there 1.05, but actually I'm going to make use of the calculator's memory function and use the exact value that's stored in the calculator. So if I put 1/2 times 2 squared times by the answer, that's going to use my previous answer, the full version, unrounded. I want to do that because it might give me a slightly different answer due to rounding error. So let's make a note of that. What have I got? 2.0943. And once again, I'm truncating, not rounding. That 3 would have become a 4 if I was rounding. I'm now going to round though. 2.09, and that would be meters squared because it's an area and we're working in meters, as we can see from the radius there. And once again, 3 significant figures. 3 significant figures is sort of my standard. If they don't specify what they want, 3 seems a reasonable degree of accuracy to me. Okay, let's continue over the page because there's more to this question. We're asked to calculate the volume of this same steel storage tank. It's the same tank, it's part of the same question, and you can see it's got a sector for its base. Now, I know that the way we calculate the volume of this kind of shape, specifically a prism, is to do the cross-sectional area times by the perpendicular height. Look out for any slope height or anything like that, but no issues with that here today. So I know that the volume will be equal to the area times by the height. Substituting into that, the area we got last time as being 2.09, and the height we can see from our diagram is 3 meters. Fortunately, there's the same units, so no conversions required, so always to think about. Again, I'm not going to use 2.09, I'm going to use the exact value that's stored in my calculator, 2.094, etc., and times that by 3, giving me 6.283 3, 1, etc., which I will now round on the answer line for 6.28 meters cubed, because it's a volume, and the degree of accuracy, 3 significant figures, is what I've used. And that's the end of question 2. Question 3. A drill drift is machined from a flat piece of steel. Here's a diagram showing that. It's a right angle triangle. I'm guessing some SOHCAHTOA is coming up. Got an angle in degrees, and there's this height here. Let's see what they want us to work out. Calculate the length of side AC. AC. So that would be this one that we're trying to find here, so I'll call it X. Right, given that this is a right angle triangle, we're going to be doing SOHCAHTOA. For SOHCAHTOA, I need to know which side is which, and it's quite easy to get muddled up on that in the heat of an exam, so I'm going to take some real care. Here's the designated angle, so this is the opposite side. This side is the longest, and it's also opposite the right angle, so that must be the hypotenuse. And it's the only one left, but it is next to it, and that's what adjacent means to. It means next to, so this is the adjacent side. Okay, what have I got? Oh, for the opposite? No, I haven't got that. Hypotenuse, yep, that one's involved. The adjacent, that's involved, and so is the hypotenuse. I don't have the opposite, I do have the adjacent. This is the one that ticks all the boxes, literally. Okay, so I need to do the cosine of an angle is equal to the adjacent divided by the hypotenuse. Right, so let's substitute into that. Cosine of what angle? 75 degrees. You don't have to show the degrees sign you're working out, but by making a note of it there, you're keeping it in your mind that you're dealing in degrees, not radians, so it doesn't hurt for a moment. The adjacent is 50. And I could put millimeters, but I'm not going to get mixed up on that. And the hypotenuse is x. Okay, so now I need to rearrange and solve this. The first thing I'm going to do is multiply both sides by x to bring x up here in front of the cos 75 degrees. That'll just leave 50 on the right. Next, I'm going to divide both sides by cos 75, and that'll leave me with just x on the left, which is what we want. And over here, 50 is also being divided by cos 75 degrees. Putting that into my calculator, 50 divided by cos 75. And, oh, I nearly forgot to check. Well, actually, I checked before I started, but my calculator is in degrees mode. That little D there means I know I'm in degrees mode, which means that's the answer that I want. 193.18, etc. And I'm going to round that to 3 significant figures, so I'm going to get 193, and the units in this question are millimeters. Need to show those for the marks, and I've got 3 significant figures. Let's just have a look to see if that's a realistic answer. If this is 50, could that be about 200? Well, potentially. I mean, it's not drawn to scale, but it's in the right sort of ballpark. That looks a bit bigger than that, a couple of times bigger. 50 times by 4 would be 200. Yeah, that fits. Let's just have a quick look at what would have happened if my calculator would have been in radians mode. So let's put my calculator into radians mode. Now you'll notice there's a little R up there. If I now work out that, I get 54. Do you know what? That's actually, unfortunately, plausible. You could think, yeah, 54 potentially. I mean, personally, I would say it's a little bit on the small side. It's not the right answer, so of course it is, but it's plausible. Sometimes when you use radians, you'll get a wildly impossible answer that will make absolutely no sense. So just do be careful. Make sure you check that it is in the correct mode by looking at the top line there and seeing if there's the D or the R or indeed the G for gradients, which we haven't even looked at in this course yet.
Question 4. The diagram represents 4 coplanar tension forces acting on a joint in a structure. And here we see those 4 forces. 26 newtons, 8 newtons, 32 newtons, and E, some unknown force. And the angles here, they're all measured relative to the horizontal rather than the vertical. And it says they're tension forces, they're all pulling outwards. You see the arrowheads on those. So I think we've had a good explore of that diagram. Let's see what they want us to do. Calculate the horizontal component of the equilibriant force E. Now there's a couple of important things here. The first one is to do with horizontal components. This 26 newtons is pulling a bit up and a bit to the right. There's an upward part and a rightward part if you sort of divided them out or resolved them into their components, as that's known. And we only care about the horizontal components. So we're going to get the horizontal component of this, how much it pulls to the right. This 8 newtons, we won't care about how much it pulls down, we'll just care about how much it pulls to the right. This 32 newtons will pull to the left and down, so we'll just worry about the lefty bit. And the equilibriant force E, equilibriant is E, that's going to pull to the left and up, but we only care about how much it pulls to the left. Equilibriant is the other one. That means that this is all balanced out. It's not going anywhere, there's no resultant force, everything is balanced and equal, which means that the horizontal components will also be in equilibrium. In other words, the left-hand bit of the 32 plus the left-hand bit of the equilibriant will equal to the right-hand bit of this 26 and the right-hand bit of this 8. So we can form an equation with that and solve it. And that's what we're going to do. So the first thing I'm going to do is the horizontal component of the equilibriant. So I'm going to call that E subscript H, the horizontal component of the equilibriant. And what I want to do now is I want to say that I'm going to take this 32, but just the part that pulls to the left, and add that on. I'll put that here in a minute. And then that's going to be equal on the other side of the equation to the part of this 26 newtons that pulls to the right, which I'll put in here in a second, and the part of this 8 newtons, ignoring the bit that pulls down, just the bit that pulls to the right, and I'll add those up there. So this is what we want to fill in. We want to fill in the horizontal components of these 3 forces, and we're looking for the horizontal component of the equilibriant. So, how do I find a component of a force? Well, if I was to draw in the components, you might see that I've got the vertical component there, and there's a horizontal component going across here. And if you know your vectors, if we put these nose to tail, they would end up giving us the same force. And that would make a right angle triangle, meaning we could use trigonometry, because the vertical and the horizontal and the vertical are at right angles, so it's a right angle triangle. There is, however, a shortcut. If I look at this force for the 26 newtons, it's 20 degrees off the horizontal. If I rotate my pen to represent the force, that angle is decreasing. You could describe that as the angle as being closed, 20, 19, 18, 17, etc., until it hits 0. If you are closing an angle, you use cos. So in this case here, to get the horizontal component, I would use cos. If I instead open the angle, 20, 21, 22, 23, 30, 40, 50, 60, 70, 80, 90 at the top, I would have to use sine. In this case, we'll see whether we're using sine or cos for each case. So for this first one here, this 32 newtons, am I opening or closing that angle of 60 as I take it to horizontal? Well, I'm closing that angle there, so I'm going to have 32 cos 60 degrees. Cos begins with C, close begins with C, that's how I remember it. Over here, this 26 newtons, to take it to the horizontal, that 20 degrees, I have to close that down. So again, that's cos. And it's 20 degrees. And this 8 newtons. Again, to get it to the horizontal, up here, I have to close down that 70. So that's 8 cos 70 degrees. Now in all three cases here it's been cos, which for a teaching example isn't ideal. It'd be nice to show you some where we had some sines in there as well. And it's not always that horizontal gives you cos and vertical gives you sine. It's just that all of these angles are measured between the force and the horizontal. And if we want the horizontal, then it's those angles that we'd have. If I wanted the vertical in these cases, I'd have to open the angle. If the angle had been measured from the vertical, it'd be the other way around. But let's carry on with this question rather than thinking about what else we might see. We've got our horizontal component of the equilibrium here in an equation. I can now rearrange this to get the values that I'm after. The horizontal component has got this added on, so I'm going to subtract that over to the other side. First, I'll just copy out what we already had. And I'm subtracting that 32 cos 60 to the other side. So, we've rearranged it. Now let's enter into the calculator. First of all, check that we're in degrees mode. The letter D is there. 26 cos 20, 8 cos 70, minus 32 cos 60. 60 is just under there. Hitting equals, we get 11.168, etc. Rounding to, I guess, three significant figures, 11.2 newtons to three significant figures. Question 5. The rate of discharge of a capacitor can be represented by the expression e to the power 2x equals 6. Solve the equation to find the value of x. Show evidence of the laws of logarithms in your answer. So let's start out by writing out the equation. E to the power of 2x equals 6. That's our starting point. The first thing that I'm going to do is I'm going to take natural log of both sides. That will be ln e to the power of 2x is equal to ln of 6. Now, the first thing I'm going to do after taking logs is I'm going to apply one of the log laws, which is if we've got a power up here, we can take it out front as a coefficient. So I'm going to do that now. And that is satisfying their requirement for the evidence of log laws being shown. So the e no longer has the power of 2x. I've brought that out in front as a coefficient. The next thing is, I know that natural log of e equals 1, and 2x times 1 is just 2x. And since I want x by itself, I need to divide both sides by 2. It's important to note that's not equal to ln of 3. It's a different way of calculating it. We need to do the log first and then divide by 2. Now we've got here, let's use our calculator to work out the value and evaluate this. So we get 0.89587, etc., which we can round as 0.896 for three significant figures. And that completes section A.